Welcome to the Guide to Subnetting, where we'll transform this technical topic into something you not only understand, but master. This isn't just another boring IT video. This is Subnetting reimagined. Don't forget to like, subscribe, and hit the notification bell to stay updated. Overview. In this video, we will cover definition of subnetting. What does subnetting mean? Why split network into subnets? Hosts, subnet mask. How to divide, subnetting. The math behind it. 2 to the power of n-2. Terms, real-world example, practice exercise. Recap. Subnetting can be confusing, but think of it like splitting up a pizza, your network, into slices for different people, subnets. Definition of subnetting. Subnetting is the process of dividing a large IP network into smaller, more manageable pieces called subnets. It helps organize networks, improve efficiency, and enhance security by assigning each group or department its own range of IP addresses. Using the network 172.20.00/16, let's explore subnetting and its key components. Why subnetting? Imagine you have a big pizza, your network 172.20.00/16, and you don't want everyone grabbing random slices. You will need to divide your network pizza among different groups. A. HR department. B. IT department. C. Development team. D. Management office. Subnetting slices your network into organized, efficient, and secure pieces. For example, HR gets one subnet, IT gets another. Everyone gets their slice. No fighting over resources. Scenario: we need to subnet the network 172.20.00/16 into smaller subnets for the following requirements. Subnet A, 500 hosts, HR department. Subnet B, 200 hosts, IT department. Subnet C, 50 hosts, development team. Subnet D, 10 hosts, management office. We'll use variable length subnet masking, VLSM, for efficient IP address utilization. Sit tight, this will be discussed later in the video. Instead of everyone grabbing random pieces, which would cause chaos, subnetting divides the pizza into neat slices, giving each group their own portion. This makes your network organized, efficient, and secure. What does 172.20.0.0/16 mean? 172.20.00. This is the starting address of your network, like the street name of your neighborhood. 16. This is like saying, I'm reserving the first 16 blocks for my network. It defines how many addresses are in your network. This is where subnetting starts. Think of 172.20.00 as the street name for your network. The /16? That's the zoning law, telling us how many houses, IP addresses, can fit on this street. 65,536. Crazy, right? Public versus private IPs, 172.20.0.0/16 is a private IP range, RFC 1918. Private IPs are used for internal networks and cannot connect directly to the internet without network address translation, NAT. IPv4 addresses are limited, leading to the adoption of IPv6, which simplifies subnetting with fixed sizes. Public IP address ranges. Important things to note. Public IP ranges exclude private IPs, as defined by RFC 1918. Class A's 127.x.x.x is reserved for loopback testing and is not used for public networking. IPs like 169.254.x.x are reserved for APIPA, automatic private IP addressing, and are not public. Public IP addresses are assigned by regional internet registries, e.g., ARINRIPEAPNIC. Here's a representation of a diagram showing both private and public IP ranges. We won't cover this fully because we will derail from subnetting. This layered view organizes both public and private IP ranges for a clear understanding of how IPv4 is structured. 172.2000/16 breakdown IP address, 32 bits, split into 4 groups of 8 bits, octets. 172.2000/16 in binary, first 16 bits, network, last 16 bits, host. Binary representation is what drives IP calculations, and each octet is just a readable chunk of 8 bits. /16 reserves the first 16 bits for the network. Remaining 16 bits are for devices' hosts. /16 reserves the first 16 bits for the network. This means the first half of the IP, network part, is fixed. The last 16 bits, host part, provide flexibility for devices. The host part can vary from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 to 1, 1, 1, 1, 1, 1, 1.1, 1, 1, 1, 1, 1, 1, 0. 65,536 addresses. Formula: 2 to the power of 16 equals 65,536 combinations of ones and zeros. Usable: subtract 2 for the network and broadcast addresses. 65,534 usable IPs. People often forget these 2 reserved addresses. That's how many hosts fit in this network. The left diagram breaks down. 1. The network part, fixed, unchangeable, defines the network, e.g. 172.20. 2. The host part, changeable, allows assigning unique IPs to devices in the network. The right diagram breaks down the example of subnets within 172.20.0.0/16. If we split the /16 into smaller subnets, the /16 network is like a neighborhood, and each subnet, e.g. /24, is like a block within the neighborhood with its own houses, hosts. Pause the video and study. Why split it into subnets? A, B, C, D. HR has 500 devices, IT has 200, development has 50, and management has 10. Now, why slice this pizza in the first place? 3 reasons: organization, efficiency, and security. For example, HR's data shouldn't mix with IT's, and development needs its own space. Subnetting keeps everything neat, optimized, and safe. It's like giving each department its own office in a skyscraper. Instead of giving all groups the whole pizza, wasting addresses, subnetting chops it up. Each group gets just the right size slice, leaving no leftovers. Hosts, and what are they? A host is any device on the network: a computer, phone, printer, server, etc. If HR has 500 devices, they need a subnet that can handle at least 500 hosts. Subnet mask. What is it? Definition of a subnet mask. A subnet mask is a 32-bit number that divides an IP address into 2 parts. 1. Network portion identifies the specific network, fixed. Second host portion identifies devices, hosts, within that network, variable. The subnet mask determines which part of an IP address is reserved for the network and which part is available for assigning to devices. Think of a subnet mask as a line drawn between your pizza slices. It tells the network, hey, this part is for the street name and this part is for the house numbers. For example, 255.255.254.0 is a /23 mask. 23 bits for the street, 9 for the houses. Visualize binary to decimal conversion. This is a flow diagram showing how a subnet mask like 255.255.254.0 translates to /23 in CIDR notation, 255.255.2540 to binary. Count of ones equals 23. Common subnet masks. Here is a small table for quick reference. Next to these blobs is a CIDR notation table, showing how IP addresses are divided based on the subnet mask explanation of columns. CIDR, notation for the number of bits used for the network. Subnet mask, the equivalent dotted decimal format of the CIDR. Network bits, fixed part of the address for the network. Host bits, remaining bits used for devices, hosts in the network. Total hosts, total number of IP addresses, 2 to the power of host bits. Usable hosts, total -2. Network and broadcast addresses are reserved. This table helps you quickly identify how many IPs you get with each CIDR notation. How to divide the pizza. Subnetting. Step 1. Determine subnet mask for each requirement. Each subnet needs a subnet mask that can accommodate the required number of hosts. The formula for determining the number of usable hosts in a subnet is 2 to the power of n-2, where n is the number of host bits. We start with 172.20.0.0/16, the big pizza, and divide it into slices. We can divide IP ranges into subnets based on the number of hosts required. Subnet A needs 500 hosts, which requires 510 usable addresses, so it is assigned a /23 CIDR with a subnet mask of 255.255.254.0. The address range for subnet A is 172.20.0.0/255.255.254.0, 172.20.1.255. Subnet B, requiring 200 hosts, uses a /24 CIDR with a subnet mask of 255.255.255.0, providing 254 usable addresses in the range 172.20.172.20.2255. For subnet C, which needs 50 hosts, a /26 CIDR is assigned, offering 62 usable addresses with a subnet mask of 255.255.255.192 in the range 172.20.3.0/172.20.3.63. Lastly, subnet D, requiring only 10 hosts, uses a /28 CIDR, providing 14 usable addresses with a subnet mask of 255.255.255.240, and its address range is 172.20.3.64-172.20.3.79. Each subnet is tailored to efficiently utilize the IP space while meeting specific host requirements. Step 2. Assign subnet ranges starting from 172.20.00/16. We allocate each subnet sequentially. What are these terms? 1. Network address, the starting point of the subnet, e.g. 172.20.00 for subnet A. Second usable IP, the first address devices can use, e.g. 172.20.01 for subnet A. 3. Last usable IP, the last address devices can use, e.g. 172.20.1254 for subnet A. 4. Broadcast address, a special address used to send messages to all devices in the subnet, e.g. 172.20.1255 for subnet A. The math behind subnetting. Math time. Don't worry, I'll make this painless. The magic formula is 2 to the power of n-2. This formula helps you figure out how many hosts fit in a subnet. N equals the number of bits for hosts. Subtract 2 for the network address and broadcast address, special addresses you can't use. Why? Because we subtract 2 addresses, one for the network itself and one for broadcasting. Example, a /23 gives 510 usable IPs. Boom. Challenge, pause this video. Grab a pen. How many hosts can you fit in a /26? Hint, 2 to the power of 6 equals 64, subtract 2, and voila. Post your answer below in the comments. Here's the breakdown for each subnet, showing the calculation and details. Step-by-step explanation for each subnet. We needed to subnet a network 172.20.0.0/16 to accommodate different numbers of hosts. Our design resulted in 4 subnets. Subnet A needed to support 500 hosts. We used a /23, providing 510 usable addresses, 172.20.0/172.20.1.255. Subnet B required 200 hosts. A /24 gave us 254 usable addresses, 172.20.2.0 to 172.20.2.2.555. Subnet C needed 50 hosts. We used a /26, providing 62 addresses, 172.20.3.0 to 172.20.3.63. Finally, Subnet D required only 10 hosts, so a /28 provided 14 addresses, 172.20.3.64-172.20.3.79. This breakdown shows the logic and math behind subnetting for each group, as well as approach efficiently allocated IP addresses, minimizing waste while ensuring each subnet had sufficient capacity. Step 3. Verify allocations. Subnet A uses 512 total addresses, 2 reserved for network and broadcast. Subnet B uses 256 total addresses. Subnet C uses 64 total addresses. Subnet D uses 16 total addresses. Total allocated addresses: 512 plus 256 plus 64 plus 16 equals 848, which fits within the available range of 172.20.0.0/16, 65,536 addresses. Troubleshooting example. If a /24 mask is applied to a network needing 300 hosts, it will fail because 2 to the power of 8 minus 2 equals 254 usable hosts, which is insufficient. Original 172.20.0.16. Binary 10101100.00000000000 subnet 172.20.0.00/23 binary 10101100.00000000000 host bits reduced. Imagine HR has 500 devices. They get their own subnet to ensure organization, no collisions. They can have custom rules, e.g., block IT from accessing HR systems. Security. Each subnet can have its own firewall. Without subnetting, HR's devices might mix with IT or other departments, causing confusion and security risks. Subnets map directly to VLANs in most networks, enabling logical isolation over shared physical infrastructure. In AWS, subnets are used to segment resources within a VPC, virtual private cloud, improving security and resource allocation. Practice. Imagine you are segmenting a corporate network. Subnet A, HR department. Subnet B, IT Department, Subnet C, Development Team, Subnet D, Management Office Practice, Exercise given 172.30.00/16, create subnets for 1. 300 hosts, 2. 100 hosts, 3.25 hosts, 4.5 hosts. Leave your answers in the comments. Steps 1. Calculate how many bits are needed for each group using 2 to the power of n-2. 2. Assign subnets starting from 172.30.0.03. Write down the network address, usable range, and broadcast address for each subnet. VLSM, Variable Length Subnet Masking. VLSM allows subnets of different sizes to exist within the same larger network. VLSM ensures efficient use of IP addresses, especially in networks with varying device counts. Supernetting, CIDR aggregation. Supernetting combines multiple smaller networks into a larger block, reducing routing table size. Combining 172.20.0.0/24, 172.20.1.0/24, and 172.20.2.0/24 into 172.20.0.0/22. IPv6, Subnetting Basics. IPv6 makes subnetting simple. Every device gets a /64 subnet. No more 2 to the power of 2 headaches. Plus, its massive address space means you'll never run out of IPs, even if every grain of sand had its own address. Fun fact: if IPv4 is a sandcastle, IPv6 is the Sahara Desert. Which would you rather manage? Type sandcastle or desert in the comments. Why IPv6 is different. Fixed subnet sizes, e.g. /64 for hosts. Huge address space, 128 bits versus 32 bits in IPv4. IPv6 transition, dual stack and tunneling. Dual stack, run IPv4 and IPv6 simultaneously. Tunneling. Encapsulate IPv6 in IPv4 packets. Choose based on network complexity, cost, security, performance. Subnetting for WAN, wide area network. Links. WAN links only need 2 IP addresses, 1 for each end of the link. Use /30, 4 addresses, 2 usable, or /31, point-to-point link, 2 total, no broadcast. 1 link 1, 172.20.4.0/30. 1 link 2, 172.20.4.4/30. Routing between subnets. Subnetting isolates networks, but how do they talk to each other? Enter routers and layer 3 switches. These devices act like translators between subnets. Each subnet has a gateway, like a border checkpoint. Step-by-step example. Subnet A, 172.20.0.0/24. Gateway, 172.20.0.1. Subnet B, 172.20.1.0/24. Gateway, 172.20.1.1. A device in Subnet A sends a packet. It hits the router, which says, "This belongs in Subnet B," and forwards it. Recap: what did we learn? Subnetting divides large networks into smaller, efficient, and secure subnets. A subnet mask defines the boundary between the network and host portions of an IP, with CIDR notation simplifying this, e.g. /24. Subnetting ensures optimal IP usage by allocating ranges based on host needs, using the formula for usable addresses. For example, 172.20.00/16 can be split into /23 for 500 hosts, /24 for 200, 26 for 50, and 28 for 10. Subnets communicate via routers or layer 3 switches using gateways and routing tables. Advanced methods like VLSM optimize space, while IPv6 simplifies subnetting with fixed/64 sizes and vast address space. Understanding binary representation, private public IPs, and troubleshooting ensures efficient network design and operation. Subnetting is all about dividing networks for better organization, efficiency, and security. Use CIDR to size your subnets. Calculate hosts with 2 to the power of n-2, and route traffic with gateways and routers. Practice is key, so look in and start slicing those network pizzas. Congratulations, subnetting champion. You've just unlocked a skill that powers the internet. Like, subscribe, and share if this video made subnetting fun. And remember, in the world of networking, knowledge is the ultimate bandwidth. See you in the next video.